All right, let me know if you...
Also record,
Oh, shoot, yes. Thank you.
of course.
Double check. You good?
Checking. Yep, we are live.
All right. Okay, hello everyone. Welcome to today's special episode of Quadcast. I am your host, Tim.
And this is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. If you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode and we'll get to them. And also, we're in the process of making shorts. So if you have any requests on sub 1 minute explanations of things that you're interested in, submit them during the episode and we'll also take that into consideration. So without further ado, let's get to it, Tim. Yeah, this Nobel Prize was really interesting. Probably, definitely broke away from the mold. It was given to two people, Geoffrey Hinton and I think John Hopfield, yeah, John Hopfield, for their work in neural nets, which is actually really surprising. There's been a lot of controversy over this Nobel Prize that it's not physics related and a whole bunch of other things. So I guess Tim, maybe to pass this off to you and kind of get your high level bird's eye perspective on this. Like, do you think that this is even related to physics? Like, what is this? Like, neural nets is more of a computer science thing from last time I checked. So why is the physics prize being given to computer scientists?
Yeah, let me just say that I can definitely see both perspectives. Like, I have talked to colleagues, physicists, who were very surprised, and they're like, what the heck is this year's Nobel Prize? What does it have anything to do with physics? I've also known people who have worked with John Hopfield himself, and I would say John Hopfield is definitely a physicist. He's professor emeritus in the physics department at Princeton. But Geoffrey Hinton, I'm sure many of the machine learning folks will know, he's known as the godfather of AI, and he is definitely not a physicist. He's a computer scientist, professor that he has done a lot of work on really foundational stuff, like backpropagation, development of some of the neural net techniques and whatnot. But anyway, if you go to the Nobel Prize press release, you will note that they specifically point out two different pieces of work. The first one is the Hopfield network, attributed to John Hopfield. And the second one, the Boltzmann machine, attributed to Geoffrey Hinton. And the funny thing is, if you talk to both physicists and like machine learning practitioners alike, they might have no clue what the heck these two things are. So that's sort of the funny thing. But let me just say this. If we were ever to award the physics Nobel Prize to machine learning and AI, these two models are probably some of the closest to physics, if that's a thing. So from that lens, if it has to be done, I feel like that's like, the most reasonable choice. But we can go into details on exactly what these models are.
Yeah. So before we dig into that, I mean, one kind of pushback, as you can probably tell by my bias, is like, does that mean that there was like nothing notable in physics that was discovered? Because these aren't like physical phenomenon or like grand unified theories or things that we typically talk about on our podcast show. This is very different. So I'm wondering, like, does this mean that physics is like the contribution of physics is actually decreasing and it's
Oh,
getting like less meaningful?
absolutely not. And I think, if memory serves me right, there have been many notable discoveries. For example, the Horizon Telescope, we saw the first image of a black hole, even though it's kind of reconstructed using computer vision, whatever. That's notable, obviously. And there are some continuous improvement of existing physics experiments and theories, And the other one is there have been a lot of cosmological measurements, like detailed precision cosmological measurements from the afterglow of the Big Bang, known as the cosmic microwave background. There has been, we've gotten much better at measuring things like the rate of expansion of our universe, composition of the different matter, and stuff like that. And also, not just on cosmology, right? Like on the front of quantum computing, there have been notable advances in recent years. Like Google, I think oh God, is it Google or I think it was Google. There have been like some breakthroughs in quantum computing simulation. Like it was all the rage some years back. They simulated a wormhole on like a little quantum computer, or they simulated time crystals, like periodic time, which is impossible in real life, but very, very interesting. Like these are just some of the small examples, right? The list goes on and on and on. Like I would say there are a lot of worthy candidates, but for some reason they were not chosen in favor of AI. So I think probably that's the larger controversy that's in there. People are like, well, why now? Why AI?
Yeah, yeah, and I'm sure we'll dig into that as we go through this. So yeah, it's interesting that you mentioned that neural nets, like the architectures that are responsible for like ChatGPT, Claude, and all these different large language models, is not what the Nobel Prize was given for, but rather these two separate or maybe connected rather. We'll see as we go along. Ideas that most people in the machine learning community haven't really come across. So why don't we dig into that? Let's start with Hopfield networks. Probably I would assume named after John Hopfield. And so what are those like? What is the significance of that?
Yeah, so Hopfield network, it's what you would call like a precursor to neural networks. This is back in the
Mhm.
days like 1970s. I forgot the date, but you can look at the publication record.
Yeah.
And also there were controversies on who developed this model first. I think there were. I'm not gonna go into that. Okay, like it's all over
Mhm.
Reddit, Twitter. You can check it out. Like, did they cite them? Is Hopfield really the first one coming with Hopfield network? But anyway, at least he popularized it. So what's the idea? This is kind of like a pre-neural network era, and people were kind of confused. Like, oh, I guess the motivation wasn't so much of getting machine to work, but trying to understand how humans can think about stuff. Um,
Mhm.
so the important bit was it was discovered that neurons can be inhibited or excited. And because of that, you can approximate it by zeros and ones. The neuron is on or off. And the
Mhm.
idea is, are there ways to kind of approximate the behaviors of neurons and see that this simple behavior of on and off is able to do complex computation? Like technically we're having this conversation and it's because neurons are
Mhm.
firing on and off, right? So Hopfield
Mhm.
network was one of the initial attempts. It borrowed ideas from zeros and ones in physics, which we'll go into. This is called spin networks. You can say, well, where does zero and one arises in physics? And this is spin networks in magnets and whatnot. You can say, inside a magnet, we can go into the more details later. This is like how magnetic hard drives work, ones and zeros. And if you look at a magnetic hard drive, it can store data, right? So
Mhm.
Hopfield kind of take this idea and say, well, what if neurons are kind of like that, ones and zeros, and add some very natural laws of physics. Say that, hey, if one neuron fire, it might cause neighbor neuron to also fire or not fire, for that matter. And he showed that if you just have this very simple pattern, neurons are able to remember things, like and I would say in terms of physics, this is actually quite physical. Maybe in the subfield of neurophysics, and Hopfield network actually become very popular in the neuroscience community, and it's one of the leading candidates for describing, maybe how memory really works. And so that's what Hopfield networks are.
So what you're saying is that there's this model of neurons that are all interconnected with each other, and these neurons can either be one or zero, and based on the way in which they're configured, it's essentially can be like storing a memory. Or am I trying to understand that correctly?
Yeah, so in going into more details, you can think of it as a machine learning model, right? The idea is you have these neural connections. The connection itself is the network, right? And if the network sees a bunch of images, you can train the neural network, and you can update the strength of these connections. You can also kind of imagine it biologically, right? Like we have our brain. As a kid, we don't know anything, but we see the world, and some of the neurons make connection with one another. So that's like training the network. As we see stuff, as we see pictures, images, whatever. And it also gives you a mode of retrieving that data by just firing of neurons. So imagine I see like 1011, like a binary data into the network, and I train my model. Then I can and I can retrieve that memory as long as I feed it in something that's similar to 1011, maybe like 1010, a small error. So the Hopfield network has two properties. You can train it to store memory, and you can run it, inference, in machine learning lingo, to retrieve the memory, right? And that's what it does. This is kind of like the, I don't know, like a precursor to the neural networks.
Mm-hmm. Could you say like the mechanism is similar? Like, let's say I'm hearing a song and I hear maybe like the first 5 seconds of it, and I'm like, oh, yeah, I remember where that's from. So effectively, a sound wave comes in, my neurons fire in a specific pattern, and then I'm able to complete the rest of the song, or like I'm able to identify, oh, this like portion of this pattern belongs to this thing.
Yeah, exactly. And what's interesting is that the law they use, we physicists have studied before. This is how the electrons in a magnet will work. The spins of electrons can be zeros or ones. They're quantum mechanical, and they have similar behaviors. They can flip up and down, up and down. And he just borrowed the equations and say, hey, what if neurons behave kind of like that? It can flip zero. Maybe you listen to Taylor Swift. I don't know what's a popular song. The beginning, the intro of some song, and there's 0 1 1 0 0 1 firing in, and you're like, and then your neurons start firing, and lo and behold, you remember the rest. Kind of like ChatGPT a little bit, I guess, right? You recall the memory.
Yeah.
It's a generative model, and maybe. I guess the relationship to ChatGPT and all these fancy generative models may be one of the reasons why all of a sudden people are bringing up Hopfield networks. That might be one of the reasons.
Yeah. So we can essentially think of there's this connection between memory and Hopfield networks. I want to move on to the other one, which I think is Hinton's contribution, which is Boltzmann machines. Before this Nobel Prize was given, I had never heard of Boltzmann machines. So maybe we can walk the audience through like what is the Boltzmann machine, is different than Hopfield networks, and then what's the significance of it?
Yeah, I would say Boltzmann machine. The detail, the name is apt. So what Geoffrey did was he took Hoffield's idea. This is like a few years later, the original paper, and he thought that one of the problem of Hopfield network is that it's a little too rigid, because it's a model for memory. It's supposed to be rigid because you're supposed to perfectly recall something, maybe with a little bit of error. But that's not helpful. Like imagine you go to ChatGPT. The only thing it can do is just recite like New York Times articles. Like that wouldn't be very generative, right? Like it's not able to create poems and stuff. So the idea is Professor Hinton thought, we need to get the model to explore a little better, to be a little less rigid. So he borrowed ideas from thermophysics, basically. He effectively turned up the temperature on the Hopfield network. You can think of Hopfield network as something that's very cold, frozen, at absolute zero temperature. He just dialed up the temperature and let the laws of thermophysics flow into the network. And as a result, he's able to get the Boltzmann machine to generate new stuff, basically. So the Boltzmann machine becomes a little more, has the ability to generalize better than Hopfield network.
So what you're saying is I could loosely think of it as a Hopfield network, like with some element of stochasticity or randomness.
Yeah, exactly. So this is sort of before the modern machine learning era, right? Like now, of course, nowadays we have stochastic gradient descent. We optimize neural networks by injecting it with noise, and so that it wiggles, so it doesn't get stuck in bad minimas and whatnot. But that idea was not fully fleshed out back in the days. So so Hinton thought that, hey, look, nature is a brilliant machine for finding minimums, right? Like if you take water and boil it, it will find, well, it will try to maximize entropy, which you can reframe it in as minimization of something. Physics just works. It just boils, right? Like it doesn't go through a computer. It just does it, right? So he just brought the idea to, well, his contribution is twofold, right? First, he make the model to make it a little more flexible, and second, he added this idea of stochasticity to allow it to be able to optimize better, right? Yeah.
So I just want to take a quick moment and sort of appreciate this minimization thing and connect it to what we're talking about. So could you view every physical process based on the way we've modeled it so far as like minimization of some quantity? We don't necessarily have to get into what that quantity is, but can be formulated as such.
Yeah, that is indeed true. If you take some classes in physics, graduate, undergraduate, you realize that a lot of the ways nature works is, loosely speaking, minimization of something. Like the way planets are moving, you can think of it as the minimization of what we call the action principle, right? Or the Lagrangian, but I don't want to go into details of these technical things. Or if you give me like a noisy system, like a thermodynamic system, it will try to maximize the entropy. Or if you take negative entropy, it's minimizing it, right? And the maximum entropy principle can be reformulated in terms of minimization of free energy in open system. It's the same. It's just a transformation of the entropy. It becomes a free energy now, and it becomes a minimization of it. So I would say the Boltzmann machine, if you look at the paper, it's literally like you could, in principle, like create this system not on a computer but in real life, like and literally dial up the temperature, because the laws it uses is literally thermodynamics, right? So it will settle. So what Boltzmann machine that is also sort of like memory recall, but it's able to generalize. Like if you remember a song, like Happy Birthday, but then you feed it in something that's not quite Happy Birthday, it's able to like generate notes that are a little different, but also novel, right? So that's what it does, because it's got a little bit more temperature. It's able to, well, in machine learning lingo, it actually computes the entire probability of your data, so you can sample different notes like ChatGPT does. So in some sense, it's kind of like the grandparents, the great grandparents of ChatGPT. It might be a stretch, but like you could say that, I think.
Yeah. So what I'm getting from this is that it's more robust. So for instance, if you were to feed in like a noisy signal into Hopfield networks, it might reproduce the wrong memory. So for instance, if my brain was a Hopfield network, and like say I was listening to a song and there was a lot of car sounds and stuff like that, and it got all muddled, and maybe I heard different words, I might incorrectly say, oh, it's this song, but when actuality it's a completely different song. Versus Boltzmann machines have a sort of robustness built into it because they can explore more, and what I'm seeing is not necessarily, or what I'm hearing isn't necessarily like what it actually is, and so it'll help me explore different possibilities. Is that an apt way of summarizing that?
Yeah, that's sort of correct because Hopfield networks are designed to be exact. Like it's an exact memory recall. If you have two memory that's
Mm,
too similar, it's a well-known
mm,
problem for the classical Hopfield network. Then you get something called a memory confusion. Like instead of
mm.
achieving either memory, you get some average, like some Frankenstein average of the two, right? And Boltzmann machine is a little bit better because it models the probability distribution. It tells you a little bit. Uh, it will tell you the probability of certain things happening. But so
Mm.
in that way, it makes it a little more flexible.
Got it. Got it. Yeah, that makes sense. Okay,
But
so
but
upbuild
yeah, but
networks. Yeah,
yeah,
go ahead.
but I want to caveat one thing. Like the papers that the Nobel Committee referred to are the classical version, right? Like of course, Hopfield network has more modern versions. People have improved it so that it's less rigid. And the same thing for Boltzmann machine. People have made it a little more flexible, a little closer to the modern paradigm. But these more modern work is not. They were not mentioned in the Nobel press release. But of course, I guess they probably contribute to the award in some ways. But who knows?
Mhm. Yeah. And so speaking of the more modern architectures, neural nets, transformers, for those who are, have heard the lingo many times, which powers ChatGPT and a variety of other large language models. Wanted to ask you, like, why didn't if Hinton is winning the Nobel Prize anyway, why didn't he just get the Nobel Prize in like, the neural nets, like even such a technique as backpropagation, which is for the audience who don't know about this, you have a neural net with a bunch of parameters, and you're trying to figure out the right combination of parameters to be able to give accurate results. And this is an efficient way of being able to compute these sets of parameters, so you can tune your model to give reasonable predictions. It's not all over the place. Just like similar if you were to type in ChatGPT, write me this, and it writes you something, and it's the reason it's taken on popularity. So that technique, backpropagation, which I believe he came up with, why didn't he win the Nobel Prize for that if you're going to go down this route?
Yeah, I would say it's just a matter of defensibility, right? Because if
Mhm.
you get the Nobel Prize for backpropagation, I don't think you can defend that it's physics anymore because it really just isn't physics. Like it literally just is calculus. Like at least Boltzmann machine is borrowing laws of thermodynamics and it's based on a
Mhm.
very physical model, the Hopfield network, which has literally the same physics as spin networks in magnets. So
Mhm.
backpropagation is just part of it. I think is part of it is probably political on some level. I think there's a desire to award the Nobel Prize to AI, but they need to somehow justify it within the physics Nobel Prize paradigm. So if you were to do that, then Hopfield network and Boltzmann machines are probably the closest thing. So from
Mhm.
that lens, yeah, I can see the reason.
But I could argue that, like, Newton came up with calculus and physics, and those are both intimately connected to each other. So I guess maybe we're drawing, pulling hairs at this point. Uh, but anyway, yeah, that I mean, what you're saying makes sense. So we've been talking a lot about this notion of spin, which you don't necessarily have to get into, but you mentioned spin networks, neurons turning on and off. So can we describe the connection between these models and the brain a bit more? Maybe you might be able to mention Ising models, if that, unless that's taking us down a major rabbit hole.
Yeah, I think it's quite simple. Like, the concept of Ising model is quite simple. So you just have to remember that in physics, electrons have spins, and spins can only be plus a half or minus a half. That's all you need to
Can
know.
we, Tim, before we continue this, can we just give an analogy of what spin is, even though it's not actually what might be happening, but just some sort of visual to really, describe what you're about to describe.
Yeah, the best analogy is probably like a little tiny spinning top. Like if it
Hmm.
spins clockwise, then it's plus positive orientation, and if it spins counterclockwise, it's negative orientation. But of course, the rate of spin, usually if you spin the top, you can have any arbitrary amount of spin, right? It can be 30 revolution per second, or 20 revolution per, or 25.12345 revolution per second, right? Like these are all valid units of spin. But because electrons are quantum mechanical, this notion of spin is discrete. It's plus a half or minus a half Planck unit. I don't want to go into details, but it's just what it is. Like to dig into it, we have to go through quantum physics. But this discrete nature, plus a half, minus a half, means that you can map them into zeros and ones. It's binary. It's either with it or against it. So it's ones or zeros, right? So in quite a lot of physical systems, you can kind of treat it like that, ones and zeros.
Got it. So I guess what makes you say that like this is there a deeper reason of how this is connected to the brain? I mean, it seemed kind of like a leap of faith to say, oh, because like electrons have this spin, then we can treat neurons. But neurons, is like made up of like a whole bunch of particles, protons, neutrons, and electrons, of course, but those have very complicated dynamics. So what I guess like what's the defensibility of being able to make that leap of like, oh, we'll just approximate a neuron as if it's like an electron up or down or zero or one?
Yeah, in some sense, there is no defensibility, and this is sort of the nature of innovation. It's a leap of faith. But I would say that one can be motivated by a concept, the concept of emergence and universality, basically. So in physics, we've seen time and time again that drastically different systems somehow end up with very similar properties. And this is not new. For example, if you look at waves is a good example. Like sound waves and ocean waves, or waves in a guitar when you pluck the string, they all obey the wave equation. You say like, well, gee, like these are totally different things. Like you don't have a guitar in the ocean plugging away, right? Like, or air molecules are so different from water molecules. How come? But when you zoom out, when all the relevant bits of physics, when the microscopic details are all gone, you see that the macroscopic structure converge. And I think by applying the Ising model, the physics of zeros and ones, electron spins, to the brain, the hope is that maybe similar things will happen. Maybe like if you zoom out these ones and zeros, because at the end you can approximate these things by ones and zeros, maybe a similar laws of physics emerge. And the great thing about physics is that because it's an experimental science, ultimately, you can just see if it works or not. So if it works, then great. Your leap of faith made sense.
Got it. I guess it's interesting that like we're bringing computation into this. I mean, in basically in undergrad, it seems like those are two separate fields in which you have physics that studies physical phenomenon such as charges repelling each other or quantum mechanical phenomenon, and then you have computer science or computation, which seems more abstract. We write code and just writes. And I'm wondering, like, why should physics play a role in computation? Like, what role does even machine learning have in physics also?
Yeah, I mean, I would say it's a valid question, but at least personally, when I was in graduate school, this is sort of like a bit of a niche field in physics. And they usually go under the umbrella of biophysics or mathematical physics. I mean, the idea is that a lot of systems like the brain or intelligence or cognition in general, these processes are too difficult. Like you can't, like it's probably impossible to break the brain down into individual particles, right? Like if I use quantum field theory to describe the brain, I'll never get anywhere, right? So some level of simplification must be made. And I've seen that in some of my biophysics colleague. Like you can simplify a cell to be like a unit that does very basic things. The hope is through this universality, the idea of emergence, that the laws of these important bits will somehow be linked to the laws of these simplified models, even though they're not exactly realistic, but like commonality emerges. So this is why it's kind of blurred up a little bit, right? Like biological systems are able to do computation. So one way or another, there's got to be some model of computation that are real. The question is, when we approximate it by some toy models, is it physics or is it not physics? I would say that maybe if it works, then it is physics, right? In some ways.
Yeah, this reminds me of something I heard when I was in grad school, where in material science or condensed matter, they theorists come up with these different types of models that aren't necessarily like very realistic. Prime examples like electrons hopping on a lattice site, or maybe some other really strange behavior, and then they get really excited when somebody finds material in the lab that just so happens to like follow this model. And so I think it ties to what you were saying, where you come up with this like really simplified picture and ends up just describing some physical phenomenon well, even though that may not be actually how it is, but it's almost like it's behaving that way. um, so I guess one thing I wanted to touch upon is maybe more connections between different phenomena in physics and these large language models. I think sometimes the connection may not be appreciated. One thing we had talked about in playing this episode is like the connection between ChatGPT or other language models like that, and things such as phase transitions. Maybe we can start off by describing in a nutshell, what phase transitions are and how they apply to these like really large networks of nodes that eventually produce language or text.
Yeah, and I would say, nowadays the like large language models are all hyped up, and it's interesting because nobody exactly knows what's going on with the large language models. It's so large, billions of parameters. It's doing some calculation like what the heck is going on. But there is a push to really understand it. And one thing we know is that in physics, there have been a lot of very, very large systems and very, very complicated systems. And using the tools of these toy models, approximations, and statistical physics, somehow we're able to make inroads to understand what they are. Like I guess a good example is like tornadoes. Like, it's very complicated. The fluid dynamics equations are probably so complicated that we can't even solve them exactly. But yet, you can study the more different facets of how tornadoes forms and whatnot, and this will be physics, right? And I would say, in some ways, like a tornado forming will be kind of like a phase transition. Like, we didn't have a tornado, suddenly there's a tornado, right? But of course, there are clearer phase transition, like water freezing. Like, suddenly the behavior changes dramatically. And the same thing can be said about large language model, because even just a few years back, large language models were not popular because, like, they just generate some text, but the text is not very good. But it seems like the moment you've made it big enough, ChatGPT is all of a sudden able to do these great things, interesting things. Maybe great is an overstatement, but like it can make poems, right? It can do like some basic algebra, although it does get some things wrong. And with recent improvements, it's able to solve some of the Olympiad math problems, although it sucks at some very, very basic tasks. Like, for the most part, the model just got bigger. Like, not much changed. But like, why the jump in behavior? The hope is, I think some researchers have already tried to use physics to describe, is there a connection? I think you can say that it's a phase transition. But the question is, can we use tools of physics and borrow the idea of emergence to see that, hey, maybe the behavior of large language model being able to do something shares the same mathematical characterization than like water freezing. I mean, that's the dream, I think.
Yeah, that's a trend I've also noticed where, when you increase the model beyond a certain size, it starts performing better. And I mean, I think originally when neural nets were first invented or discovered, depending on which perspective you take, I don't think they performed well at all, which is maybe they were, I think in the 1970s or somewhere around there is when they first came about, or at least appeared in the literature. And then they didn't make a comeback until like many decades later. And that was just due to increasing compute. And so yeah, it is interesting that you can take this model and just throw more compute at it and it performs better. But I mean, there's definitely talks of diminishing returns. I've seen many videos and many papers talking about the increase in performance is decreasing as you throw more compute at it. So we might be reaching a plateau potentially. Unclear though. I want to maybe a little bit talk about more of the I guess the more pessimistic side of these things, as I was alluding to in the beginning, and just ask you again, like this, like, do you really consider this fundamental physics? Because I thought the Nobel Prize in physics was like supposed to be about that. I know there's a whole bunch of other candidates, but it just
Mhm.
it just seems really really bizarre that I could see maybe even if they gave this in like economics or something, because that tends to be more human focused, but in physics of all things, which is the least anthropocentric Nobel Prize from what I've seen.
Although I'm not so sure about that. I would say that the
Okay.
Nobel Committee has always been a kind of, I don't know. I don't if iffy is the right word, but they're not necessarily consistent.
Mm,
For example, I think their mission is for the betterment of mankind. But of course, if you're a realist, you argue that, I don't know, like the discovery of gravitational merger, does that benefit mankind? Or like discovery of the Higgs
mhm,
boson, does that benefit mankind? And then you contrast these with like the discovery of transistors, or like MRI. I think that was a Nobel, right? But I could be wrong. But those were like life changing for, like, it really changes our lives compared to like
mhm,
gravitational waves. So I would say whether it is whether the Nobel Prize linked to um, the improvement of mankind is dubious at best, right? But one thing for sure is that I would say that one thing that's clear, at least the Nobel Prize committee is trying to stay relevant. That much I
mhm,
think can be said for sure.
mhm.
So maybe in an effort to stay relevant, AI is the way to go, right? So
I'd like to challenge that. I mean, I would have agreed with you until maybe like today or yesterday, but they gave the Nobel Prize in economics to three people who basically are saying that AI is just all hyped up and it's not going to lead to the increases in productivity. So from that perspective, what are your thoughts?
yeah, I've talked to physics colleagues, and I can imagine I put myself in academia and not in the data science realm. I probably would be somewhat jaded, because
Mm,
for one thing, one of the recipient was not even a physicist, like
yeah.
and like Geoffrey Hinton, like, oh, everyone knows his name in the AI community, and it's not like he's short on cash or like awards either. He's got plenty of awards, and he's probably,
Mhm,
with the AI hype, he probably makes more than enough money. So you can argue that
mhm,
Nobel Prize was supposed to be for this, like, fundamental physics stuff that that maybe wouldn't get as much attention otherwise, but like give them the recognition nonetheless. Because like, who's gonna care about the Higgs boson? You know, like for a common lay person. Although personally, I would say that that's what physics should be about. It's about fundamental discovery. Like we don't necessarily care about the implications because it could be 1,000 years from now. Who knows, right?
Mm-hmm.
But yeah, but I don't know. But on the other hand, maybe the Nobel Committee is trying to make a statement. It's trying to say that, hey, look, like to be a physicist, you don't just have to study fundamental physics. Because when in my time at Princeton, there's always this viewpoint that, if you're doing biophysics, it's kind of like not pure physics. It's like not as good in some ways, right? You're just studying emergent phenomenon. Like you're not really discovering the truth. So part of that, maybe the Nobel Committee is trying to highlight that. Like you don't have to do the most hardcore, you don't have to take the most purest point of view to be a physicist, but you can study physics relevant stuff and still be recognized like as a world class physicist. So from that perspective, maybe I wouldn't be as jaded about the award this year as I would be.
Yeah, you have a way more optimistic view than I do. I wanted to ask an audience question before we move on to our final thing. Is when we were talking about Hopfield networks and Boltzmann machines, one of the audience member asked, "What does all of this have to do with intelligence? In particular, like memory doesn't equal intelligence," is what this particular audience member is driving at. So wanted to get your take on that.
Yeah, absolutely. That's true. Like, memory is not intelligence. 100% agree. I would say you can argue that this is some of the beginning work, right? I think in order for something to be intelligent, at least it needs to remember. It needs to learn and remember what it has learned. So I think like memory is a requirement. And so that's sort of the first step. And the ideas about cognition, that's way more complicated. I don't even know if we have a general definition of what really intelligent is. But, maybe it will be, or who knows, maybe it'll be another physicist. Maybe this is like Nobel Physics 2090, who knows, right? A model for intelligence, right? Maybe, I don't know. Yeah.
Only time will tell. Yeah, so for the final thing, wanted to just ask you point blank, what does it mean to be a physicist? What does it mean to do physics, given this Nobel Prize news?
Yeah, I would say personally, my perspective definitely has shifted. When I was a student in graduate school, I definitely have this idea of purity of physics. Like there are a lot of people who wanted to do string theory, but in my mind, string theory was too mathematical. There's no. I'm always a champion. I always think that physics is fundamentally an experimental science. Like you have to link theory to experiments. So, I mean, I still think string theory is physics because in principle you can test them. But I would say in terms of purity, which I don't think it's a good idea to think of it that way. But if you do subscribe to that idea, I would say like if you want to be like really a physicist, you should have theories and experiment and link them together, right? And of course, the Nobel Prize is challenging that because like where is the breakthrough? Because I can see a lot of Nobel Prize. There have been a lot of theories waiting for Nobel Prize. Like for example, the theory of inflation. I'm sure it's Nobel worthy, but we haven't confirmed it yet. We don't know if the universe has gone through a period of rapid inflation. Kind of like our inflation, but probably a little more dramatic. But jokes aside. And there are many theories like that, just waiting for the experimental confirmation to get their Nobel Prize. But you can argue that the Hopfield network and Boltzmann machine kind of skipped that a little bit, right? But but where is the verification? But if it could ever be a verification, like I don't know if you can ever verify a Hopfield network. I mean, it works on a machine, or the Boltzmann, the Boltzmann machine model. It works on a machine. So is it like verified? So my perspective definitely has shifted. I think maybe the more modern viewpoint is based on utility. Like, can your physics principle help you understand certain things and help make progress? And if that is, if let's say if this is the take for the Nobel Committee from now on, then maybe some of the unverified theories maybe should be eligible for Nobel Award now. Maybe if they inspire something else, like string theory, if they inspire some study on condensed matter physics, maybe string theory should get a Nobel Prize. Maybe, maybe supersymmetry can be applied to materials and do some fancy things, or like some other more speculative ideas. Maybe they should be eligible for Nobel Prize. So I don't know. Yeah, so it's complicated. I think it's really trying to redefine what it means to have an experiment and have it verify and have, I don't know, have your theory do something, if that makes sense.
Yeah, no, that totally makes sense. I'll just add to that from my own experience, and just say that like I really think at a deep level that all these distinctions, and this is by no means my support for the decision to give Nobel Prize for this, but tying to what you said, the distinction between all these different fields like physics, chemistry, biology, psychology, all other social science and stuff like that, it's just artificial. There's just there's just nature, and it's doing what it's doing, and we're classifying it into these bins and categories. And I mean, now you're seeing a move towards different works of cross-disciplinariness. That's a word. And so I would just say that from my perspective, I think of a physicist as kind of like the Peter Pans of the world. Like, you sort of, in some sense, part of you never grows up, where you're just generally very curious about things. But yeah, I guess like if we're going with the purist perspective, I can see that this Nobel Prize can be infuriating potentially. So that's just my aspect to this. So I guess Tim, in our, I don't know, maybe this was your concluding statement, but I'll just say if there's anything else you want to add, and in our tradition of like what the Nobel Prize in Physics given for this work in AI related models has taught you, like any words of wisdom from that.
Yeah, I would. Yeah, I guess I would repeat a little bit of what I said, but in shortened form. I think the Nobel Committee probably has some conflict of interest. Probably they're trying to stay relevant, and some of the controversies are probably justified. But whether you like it or not, I think it is highlighting the fact that it's highlighting the fact that in this modern era, what it means to be a physicist is shifting. It is not as easy as before to do fundamental physics, and maybe there is less need for humanity to do fundamental physics, and maybe the highlight is more about emergent phenomenon. And maybe you can argue that some of our fundamental laws are emergent. Maybe all along we have always been studying emergent phenomenon, but one way or another, physics is changing, and you just sort of have to accept that. And maybe in the future, all fields will just converge into like mega science, whatever you call it, right?
Yeah, yeah. Two things I'll say to that is, one, I think if Mikey was here, he would disagree with what you said. I think he would feel like there is a need to study fundamental physics, because if you want things like warp drives, or next generation space age technology to move us from like one galaxy to another in record time, that's not you do need discoveries in fundamental physics. And then I would want to, actually, one last question I want to ask you. is given that this Nobel Prize was awarded in, my opinion, more of computer science than physics, do you think that will incentivize less, future generations, less so to get into physics and more into computer science and things, in fields such as that?
Yeah, I mean, I don't want to give too much credit on the Nobel Committee. Obviously, people don't do
Mm,
physics trying to get a Nobel Prize, but it is shifting the discussion and the culture a little bit. And sadly, I do think that it will shift the needle to away from fundamental physics, because already fundamental, being a physics studying fundamental laws is not very lucrative in any way, and you really don't get recognized very much. It's mostly for your own benefit. You feel like you want to figure out what the world is like, and this unfortunately shifts in the other direction. It's telling you that, hey, society wants to recognize physicists who study things that are relevant to humanities a little bit more.
mm,
Things that potentially will be useful. I think from the angle of utility, yeah, maybe that's a good thing, but I think that's also not the best for science, because I think there needs to be some. I mean, in the analogy of Hopfield network, right? We can't, as a society, we can't be too rigid. We need some people whose own goal is just to study physics for physics' sake.
mm.
So I hope the impact wouldn't be as big, and I hope people are still motivated to study fundamental physics, because I think it's important.
Mhm. Yeah, I think that's a great post closing statement. So on that note, I want to thank everybody for joining us, and we'll see you all next week.